So today we're going to talk about another old school mathematician. In our last couple lessons, like we were introduced to Euclid, the father of geometry. The other day when we were talking about the circumference of a circle, we heard about Archimedes. And today we're going to talk about another old school mathematician as well, very famous, for our discipline. But before we get to that, I wanted to talk to you about an art concept, actually. So you can see here, I've got these three squares up here, a pink square, a yellow square, and a blue square, right? And I wanted to talk about the art concept of negative space. Okay, so negative space in art is everything that isn't your art project. So like, for example, if my art project here were these three colored squares, these different size squares you see up here, right? Then the negative space would be all of the brown surrounding that. That would be the negative space. And I kind of like to highlight this with a kind of a, cool, interesting little negative space thing that happened, actually kind of happened by accident, which is sort of cool about it. Let me show you this. Okay. So we're all familiar with this logo, right? FedEx, shipping company, right? They get things from one place to another. And so when FedEx was starting off, and they hired this company to produce their logos and stuff, and the company was putting together these different things with different fonts, and they tried this block letter thing, and the people liked it. And then somebody in one of the board meetings said, "Hey, what's really cool about that is that there's an arrow buried in the logo." Do you see it? Do you know where the logo, where the arrow is in the FedEx logo? If you can't see it, or if you haven't seen it before, it's right here. Check it out. Yeah, right? It's hidden in there. And it actually kind of happened by accident, but then it became part of their plan. They were like, well, hey, check this out. We're FedEx, we're a shipping company. We move things from one place to another. Let's keep that logo in there. Yeah. And by the way, you will never be able to unsee that now. Every time you look at the FedEx logo, yeah, that big white arrow is going to stand out at you. So yeah, sorry, I ruined you. Not sorry. But anyway, I just wanted to share that with you. There's a really cool part of the idea of negative space in there. Well, we're going to be talking about negative space when it comes to this particular old school mathematician. Now, in our introduction to geometry, we heard that Euclid was not the first person to work with geometric concepts. He was just the first person to organize it in a very special way, in this sort of systematic, one thing builds on top of another through an entire discipline of academics. Well, the guy that we're going to talk about today also was not the first person to work with this. In fact, this concept is really one of the oldest math concepts out there. And it was actually used in agriculture. It was this idea of how do we make 90-degree angles and straight lines to keep our fields straight. And so what they would do is they would take a rope and they would tie a knot in a rope at a certain distance, fold it over, tie a knot in the rope at a certain distance that was the same. And then they would just keep doing that, tying knots in the rope at the same distance. And then when they had the same number of knots going one way and then going the other way, then they could see that they had this perfect square distance, and then they keep their field straight. And actually the Egyptians used this idea to kind of map out the base of the pyramids too. So this is an old concept of this idea of measuring the distance with these ropes. And so today we're going to be talking about the mathematician Pythagoras. And he was before Euclid. So he was about 500 BC. So we've seen Archimedes is after, and Euclid Pythagoras is before. And Pythagoras was doing something with this same idea of kind of measuring and working with squares. And so as he was playing with squares, he noticed that there was a certain relationship that exists, right? So like, for example, take a look at the areas of these squares. We just got done doing an area lesson, right? So like the pink square, what is the area of the pink square? Yeah, right. It's 9, exactly. Yeah, 9. And what is the area of the yellow square? 16, good. And the area of the blue square? Right, 25, good. Okay. So what he noticed was when this particular, here's the relationship that he saw. Okay, he said, when you have these three squares and you've got a smaller one and then a medium one and then a larger one, if you took the areas of the smaller one and the medium one and you added them together, if that area was equal to the area of the larger square, then something happened. And so like in this case, you could see here, like we had the pink square as an area of 9. Right? Yellow square is area of 16. 9 plus 16 is 25, right? You could see that the blue square, there are 25 little squares. I could cut out all the pink and yellow squares here and like paste them over the blue square, right? And then we would be able to cover the blue square in its entirety. And what Pythagoras noticed was that if you had this relationship that existed, this small area and medium area combined together to give you the same as the large area, what he noticed is you could take these squares and you could put them together corner to corner like this. And every time you put them together corner to corner, in the negative space, there was a right triangle. You see the right triangle in there, right here in the middle, right? Like there's our little right angle right there, and there's our right triangle. And so this began to develop as like, hey, look, this is present with everything. Just like when we looked at the circles the other day, and we talked about how all circles are related to the distance across them, that diameter. So there's 3 diameters and 14% of the fourth diameter, or 3.14-ish diameters in every circumference of a circle. Well, every time you had this idea of a small area and a medium area adding up to give you a big area, you always got a right triangle, right? Okay, so do you guys know what this is called? What is this called? That's right. This is called the Pythagorean theorem. That's what this is. This is the Pythagorean theorem. And so that's what we're going to be studying today. We're going to be looking at that in some detail and using that, because this is a math concept and a math skill that we use a lot in geometry. We use this a lot. So this is an important one. So let's get digging in to talk about the Pythagorean theorem. Let's talk about the Pythagorean theorem. All right. So what I had just explained to you with that example with the blue and the yellow and the pink squares is that the area of the small square combined with the area of the medium square is going to be equal to the area of the large square, right? This is what Pythagoras discovered, right? And as he was doing this, he was like, okay, well, let's talk about this generically. Like in that particular example, we had, a 3 by 3 square with an area of 9, a 4 by 4 square area of 16, a 5 by 5 square area of 25. And so he said, well, what if we just give these like generic things? And then as it's been translated into English, he said, all right, well, what if we had a square with an area with a side length of a? So then what would be the area of that square? Yeah, it would be a to the second power, right? Because it comes from a times a, or the same thing times itself, right? So this would be a to the second power. And then if he gave the middle one this b length, what would be the area of the medium square? Yeah, b squared, or b to the second, right? And then the third one would be what? C squared. Yeah, c squared, right? And so what we see happen here is the kind of abbreviation of this that comes out, where we say that the area of the small square plus the area of the medium square is equal to the area of the large square. And the reason why I go back and teach this way is because it's really important that you distinguish the difference between a squared and a. You've got to know the difference between those, right? The a squared is the area of the square that comes off the side of the triangle, whereas the a is just that single individual measurement that runs from here to here. Whether you're talking about it as the side of the square or the side of the triangle, it's the same thing, but you have to be able to distinguish those and communicate them clearly. Now, we'll just kind of summarize the little example I gave you up here. So in the example I gave you before, we'll start our problem off like this. I'm a big fan of starting problems with parentheses. And so I had given you a 3 by 3 square, a 4 by 4 square, and a 5 by 5 square. And so that would give us an area of 9 plus an area of 16 is equal to an area of 25. And so, of course, 25 is equal to 25. And that checks.
Can't you, like, if you want to find B, but you only have A and C, can't you, like, do, like, C minus A equals B?
That's a great question. We're going to talk about that in just a little bit when we get to doing the actual numbers, all right? So, I want to introduce you to some language, all right? And so we're going to write this out a little bit differently here. So we'll start with saying the Pythagorean theorem. And we're going to write this as an if-then statement. So the Pythagorean theorem actually reads this. If a triangle is right, which means it has a 90-degree angle in it, then a squared plus b squared equals c squared is a valid equation. And I'm going to underline the if and the then. So this is how the Pythagorean theorem reads. If a triangle is right, then a squared plus b squared equals c squared. All right, now let's talk about the converse and we'll just abbreviate this time. The converse of Pythagorean theorem. Converse, inverse, reverse, kind of all sort of means the same thing, okay? So we're going to say if a squared plus b squared equals c squared, then the triangle is right. Again, underlining the if and the then. Okay, what just happened with those two statements? What's that? What do you notice?
It's an if-then statement. So like, if one thing has to be true, or if one thing is true, then like it automatically makes the other thing true. Like,
well, one thing is dependent on the other, right? Like if I don't show up to work, then I don't get a paycheck, right? So, you know, and then my wife's not very happy with me either. So that's important why I come to work, right? Okay, well, let's jot that down. That's an important observation. So, an if then statement in math language is something that we call a conditional statement. So just like the other day when I was like having you solve equations and I said, okay, well, whatever you do on one side of an equation, do on the other side. But then I asked you for the formal math name and you were like, what? It's the what when you do the same thing on one side of the equation as the other when you're solving? The property of equality, right? And then there's addition, subtraction, multiplication, division, right? Okay, so when we say if-then statements, these are conditional statements. But that wasn't actually my question that I asked. The question that I asked was, what do you notice happened from the Pythagorean theorem to the converse of the Pythagorean theorem? Raise your hand and you tell me what you think you noticed happened. Yes. What flipped? Yeah, the if and the then part flipped places, right? Now you're going to hear me say this a lot in this class, okay? I'm going to use the analogy of walking on a sidewalk. Pretend that there was a sidewalk right here in front of the front row, okay? A lot of times in geometry, I can walk one way on this sidewalk and do something down here, and then I can turn around and I can walk back the other direction on the same sidewalk. This is an example of that same thing right here. So I'm saying, if a triangle is right, then a squared plus b squared equals c squared. But then I can turn around and walk the other direction and say, if a squared plus b squared equals c squared, then a triangle is right. See what I did? Okay? And so there's going to be a lot of times where we can walk both directions on that sidewalk. And when we do that, we'll put 2 asterisks here. If this is true in both directions, if our conditional statement is true in both directions, that is called a biconditional statement. So again, we're just kind of putting some formalized geometry language with some of this here, okay? So the if-then is a conditional statement, and if it's true in both directions, if we can turn around and walk the same direction or the different direction on the same sidewalk, then we have what's called a biconditional statement. Okay, so let's put some of this into application. Now, we're going to do some problems together. Some problems you're going to do on your own. I'm going to bounce around, so don't just start working things out and not paying attention. Stay with me, and then that way you're not doing more than you need to do. There you go. And then that way you're doing exactly what you do. Makes it really easy. All right, now, let's start with some instructions. Your job is going to be to find the missing squares area of the 3 squares, and then we're going to use that with our Pythagorean theorem in order to be able to find the 3 side lengths of the squares, or if you want to think of it as the 3 side lengths of the triangle, we can talk about it that way. A is going to be our smallest side, B is going to be our middle side, and C is going to be our largest side, okay? So that's how we're going to write our answers out in here. So I'm going to get a copy of I'm going to want you to use your equation line, okay? So everybody's still to use your equation line. And we are going to start with number 8. And so I'm going to put my little equation line right down here on number 8. What I want you to do first here on number 8 is I want you to write a Pythagorean theorem equation that you think will help solve this problem. Now keep in mind, when I showed you that little example of the pink, yellow, and blue squares, and we wrote it out on our paper here, it was always the small area and the medium area that meet to form the 90-degree angle, right? That's important, right? Those the small area and the medium area that meet to form the 90-degree angle. So finding the 90-degree angle is super important in what we're doing here. Okay, so you're just setting up the problem. I just want to make sure that you get it set up correctly. All right, you got your problem set up? You should have put down something that looks like that. Yes? Good? Now, the reason why we're doing this equation line here and the variables is because so often what I see happen is students just start adding numbers and then all of a sudden equal signs disappear, variables disappear. This is an equation. If you start with an equation, you must end with an equation. And you must have an equation all the way along the way, which means you've got to have an equal sign and you've got to have a variable. Okay? So it's important that you keep track of that, and this will help you keep your work organized. All right, good. So what's the next step in solving this equation? Now we're just solving equations, right? What would be the next step? Somebody raise your hand and tell me what I'm going to do next. Yeah, go ahead. Okay, so what do you get when you add those together? All right, so we get 625 is equal to c squared. All right, cool. What does that number mean?
That's like the big square. That's the area of the big square?
That's the area of the big square. Good. Well, so that's part of what we're looking for, right? So we're going to write that in here. So 625 what? Millimeters squared, right? Because that's the area of the big square. Now, that came from this side times this side. So the same number times itself, right? Okay, what question can we ask of a number to say, hey, what times itself gives us? Arjun? Yeah, the square root. Okay, so here, I have a question for you guys. What times itself gives me c squared? Tell your neighbor right now. What times itself gives me c squared?
125.
Okay, what did you say it was? Who's got it?
25.
Wrong.
What?
That's not 25, that's 25.
What's the right answer? C. Oh, because the question I asked was what times itself gives me c squared. See, this is exactly where the numbers begin to disappear, right? It's right here where students go, oh, the answer is 25, and then you just write it down, okay? But what I need to see from you is that this produces c. It's important that you understand that you're answering that same question, because once you ask that question on one side, properties of equality say you have to answer that question on the other side. Now where you put the 25 down. Okay, what does that 25 mean?
That's the answer to the long side.
The long side of what? What do you mean long side?
Triangle.
That would be the length of the longest side of the triangle or one of the sides of the biggest square, right? Fletcher, question?
I was going to say it's also like you could have said to make it for the length you don't have positives.
We could say that too. Yeah, we're not quite there, but yeah, good, exactly, right? Okay, good. So then we've asked the square root question here, and we've gotten c is equal to 25 what? Just millimeters, because it's a single length, right? Okay, so then we also have to ask the square root question of these two sides here, of these two areas to get the sides. So then what would A be?
20.
It's going to be 15 millimeters, because that's going to be our small side. And then what would B be? 20 millimeters, because that would come from our 400. Now, realistically, it doesn't really matter which one we call A and which one we call B, because they're both on the addition side of the equation. So 2 plus 3 is 5, 3 plus 2 is 5. We can flip-flop those, right? What's that called when we flip-flop the order of things in a math problem? No.
Commutative property.
That's the commutative property. That's the commutative property. Okay. Good so far? You know what I'm looking for on the problem? Question. It would, no, in this case, it wouldn't be wrong. It's fine if you put it under there. But since I specified in the instructions A is small, B is medium, C is large, if I don't specify it. If I specify it, then yeah, obviously it's not going to meet the requirements of the question. All right, so let's do number 2. So what I'd like you to do is I'd like you to write out an equation line for number 2, and I want you to do all of the work, find all of the sides, and notate it exactly like how I did, keeping your equal signs and variables present, and then we'll go from there. So you're doing number 2, ready, set, go. Okay, how we doing? Ready to take a look? Yeah?
The answer is 34.
Well, there's 3 answers, so, you know. But the answer is actually all of this. All of this is the answer. Okay, so important, I want to make sure to see your equation all the way down with your equal signs and your variables, and then to find the distances. Question, Lauren?
Do you have to write the square root or not?
Yes, I do want you to write the square root, because that's helping us remember that question, and that's how that gets us back to the side line. Okay? All right, good so far? Yes. No, I just put that on there for you. Yeah. But you can if you want. If it's helpful, you can do that. That just might make it easier that you don't stumble writing things down over here. But okay, let's talk about number 3. Start with number 3. Okay, here's what I want you to do for number 3. Let's just start by getting the problem set up, because I do want to talk to you about something before you do the problem, and I don't want you to do the problem incorrectly. So let's just start with the setup for number 3. Let's just start with the setup for number 3. Okay, you got your setup written down? That's all I want you to do is just the setup. All right, now, what you should have put down for your setup should have been this right here. Right, because what we notice is that we have the area of the small square and the area of the large square. What we're missing is the area of the medium square. Now, this goes back to Pedro's question from earlier. Would it have been okay to set up the problem like this?
Yes.
Yeah.
The answer is yes.
The answer is yes. Okay, let's take a vote. The answer is yes, it's okay to set up the problem like that. The answer is no, it's not okay to set up the problem like that. Let me see what you guys said.
If you guys say no, you're wrong.
Pedro, wait. Yes is 1.
Yes is 1, no is 2.
It's 49 to be squared.
Yes is 1,
I feel like this one
and
might
no
be
is
right.
2. No, 49 is not supposed to be squared. So
I feel like it's a trick question.
it is a trick question. The answer is no.
Ooh, I was right.
The answer is no. Let me tell you why the answer is no. Okay? So, let me tell you why the answer is no. Okay? So, what I'm going to be asking you to do is create math problems based on geometric principles. Okay? And you're going to have to name that geometric principle. So, you're going to have to set up the problem correctly and tell me why you set the problem up the way that you did. And then you're going to have to do the math correctly. So 3 parts to one of these questions. There's 3 things that I'm going to be grading. Did you set the problem up correctly? Did you identify why you set the problem up correctly? And then did you do the math? Okay, so question, right? On the left up here, I set the problem up one way, and on the right, I set the problem up the other way. So we've set our problems up. What would be the reason we give for setting up our problems in this particular case? What reason do we have for taking numbers and squaring them and putting them a couple on one side and plussing them and one number on the other side? What would we call that? The Pythagorean theorem. What is the Pythagorean theorem with letters? Say it for me.
A squared plus b squared.
It is not c squared minus b squared equals a squared or vice versa. That is not the Pythagorean theorem. Now, will you get the same result over here when you do your math? Sure, but you're going to miss this part because you didn't set the problem up correctly using the Pythagorean theorem. That's why it's not right. What actually happens with the subtraction here is what happens in the solving of the equation. So the subtracting part actually takes place over here. And so it is important the way that you write that down, because over here, you're showing me that you understand that the areas of the medium and the small square are the ones that are being added, and that the area of the large square is the one on the other side. Does that make sense? All right? Okay, so this right here is a no-no. Okay, now when you make your argument, you get the exact same thing, but you don't. You get the same result over here, but you don't get the exact same thing that I write down. And what you want is what I write down, because that's what I'm grading you on. So it's not just about the answer. Again, what you're saying is it's just about the last statement that comes in my argumentative paragraph, but that's not what we're focused on. We're focused on everything from the top to the bottom, and so I want you to be accurate when you set up your problems. You wouldn't mix up setting up problems if you're using the principle of complementary angles and change things up, because complementary angles have a specific way that we write that, and so you do need to know how to do that correctly. Okay? All right. Go ahead and finish this problem out. Go for it. Here's what you should have come up with. Again, keeping your variable through, your equal sign through, and your measurements. Okay? Questions? Make sense? Okay. All right, let's go to the back side. And we're going to take a look at question number 9 now on the back side. Question number 9.
Oh, we have to find an area.
So now you have to find all 3 areas and set up a Pythagorean theorem question to do that. So we're going to find all 3 areas. Okay, so let's start. Whoa, that is not what I wanted. I just bought this last night.
Uh-oh.
The other one I used yesterday was, oh man, yesterday was such a nightmare. Like, I couldn't write anything because my pen was broken, so I had to buy a new pen last night. Anyone want to take a guess at how much these things are?
Like 200.
$150, yeah. That's $150. Should not drop that on the ground. Okay. All right, so let's take a look at number 9. So let's start with, how are you going to set up a problem? Where are you going to start? Let's start with, where are you going to start? Where are you going to start for this question?
No, it's the opposite.
Okay, just the setup, right? Setup should have looked like that.
I'm gonna cry.
Now, you say, well, okay, well, how come you use an X? Well, that's because that's what the problem specifies here as an X, all right? And so we want to look for the variables as they're specified, and then let's use them as they're defined, okay? You should be flexible enough to be able to do that. All right, so now we're starting at the side lanes, which means we're starting at the side lanes. We've got to go out to the areas so that then we can find the other area and then come back to the side lane. That's really what we're doing here, right? So what we're doing is we're finding the area of the small square, and we're going to write that in over here.
Yes.
So this is our area of the small square. This is the area of our medium square. Then we're going to continue solving our equation. That's going to give us the area, or sorry, I said medium earlier. This is the area of the medium square here. And then we can ask the square root question of both sides of our equation to find the length of our side. See what we did? Started with the sides, went out to the areas, found the other area, used the square root question to come back to the side. That's the process. All right, I'm going to have you guys do, let's do 14. I'm going to have you guys do 14 right now.
I had a feeling you were going to do this.
You think that was one?
Like just a gut feeling. That was like creepy.
All right, so you're doing 14. I think I'm going to set my problem up. I'm going to set my problem up over here. All right, you're working on 14. See what you come up with. 14 should have looked like this. Take a look, see how you did.
Yes!
Yes? Excellent. Excellent. All right, cool. Good. Yes. No, because we're missing. Yeah, we're missing the little square. So it would be part of the addition problem.
Yeah, so it'd be a squared plus b squared.
Oh, yeah. The order you're talking about the order between what? Yeah. Again, 2 plus 3 is 5. 3 plus 2 is 5. And especially when we're using just a variable like x, then it really doesn't matter. Yeah. Okay. All right. Good. Okay. Let's put some formal language with this so that we're making sure that we're on the right track. This is why we have binders.
Another one, thank you.
There will be a lot of these.
Thank you. You don't need
Nope. All right. So, formal language to attach to some of this. So, sides A and B, right? These are called the legs of the right triangle. And the legs always meet at 90 degrees. The legs always meet at 90 degrees. Wait, always meets at 90 degrees. Always meets at. Now, we heard that before. Where have we heard always meets at 90 degrees?
Oh, for the Pythagorean theorem.
No, we heard that before somewhere. What's that?
Right triangle.
Well, not just right.
When we were finding the area in like parallel.
The area of what? Triangles, parallelogram. So what was it, Pierce? Where did we hear this?
Was it from that video where they're showing like the circles and then
Base and height always meet at 90 degrees, right? Okay, now, here's why that's important. Watch. Because now, with this type of a triangle, if I gave you this measurement, and I said find the area of the triangle, you would be able to do it. Because you could use Pythagorean theorem to find your other side length and then multiply those to come up with the area of the triangle. So see, that becomes now an extension of this problem. Now you can find the area of any right triangle given any two sides. You don't just need the base and the height in a right triangle. Only a right triangle, because we only have this tool for right triangles, okay? There are other tools for other triangles, but we haven't quite gotten there yet, okay? All right, so here's where it comes in what Kalechi had said earlier. What is side C called? The hypotenuse. Good. All right. Okay, and what we want to know about the hypotenuse is that it is always opposite from the 90-degree angle. So while our legs always meet to form the 90-degree angle, the hypotenuse is always the side across the room or opposite from the 90-degree angle. What side is always the longest side in a right triangle? Why?
Because it's one side.
Why? Hold on. Here. Okay, hold on. Here's what I say. Go ahead. How do you know that? I don't know if I agree with that. But is it always the longest? Yeah, but give me a reason. Why?
Because in Pythagorean theorem, is that how you say it? It says that the C length is always like the largest length, and then the A and B are the smallest.
How do we know it's always the largest length? Because it comes from where? The side of what? No. The side of what? No. The side of what?
A square.
Of what square? The largest square. That's why it's always the longest side. because that side is the side that measures along the largest square's area, right? Small square, medium square, largest square. That's why that diagonal exists. Okay? That's why that's the longest. Okay. Of course, we now know the Pythagorean theorem is used to find the missing side length on a right triangle, and that our formal theorem is a squared plus b squared equals c squared. Just sort of formalizing some of the things we've talked about here. Now, you will have questions where it doesn't work out to be a nice, neat whole number. And that's when you will have to round your answers to where I tell you to. In this case, we're going to round our answer to the nearest tenth. All right. You got number 1. Now, you'll notice that with this question, there are no squares around there. But what I do need you to know is that the reason these things are what they are is because of the squares that come off of them. Okay?
Wait,
it's important you understand that.
What if it's like, is it possible that like, like one of the sides, like you know how it's like a length of 8?
Okay?
What if it wasn't a square though?
But it is a square, because this is the only way that we could have this relationship exist is because these distances are exactly the same. If it wasn't a square, that relationship wouldn't exist. It wouldn't be what it is. Okay, go ahead. You're working on this one. Set that up. Okay, just number 1. That's all we're doing. Ready to take a look? Okay, let's take a look. Here we go.
Yes.
How do we do?
I got it right.
Good? Okay, couple things I want to talk about. Number 1. This probably should be, in all technicality, it should be an approximation sign. Anytime we round a number, it's an approximation. We're just going to do so many problems at times where we're rounding numbers where it's just not going to be written like that. And so I'm not going to hold you accountable to that, but I do need you to know it's an approximation. There's a difference between when we round a number and we write it as 27 pi. Okay? All right, now, I want to go back to Pedro's question for just a second, just to humor him just a little bit here. So let's say that we did have, in fact, a little rectangle coming off of here that was 7 by 2. And then let's say we had another little rectangle coming off of here that was 8 by 3, and I asked you to find the length of side x. Okay, well, remember, Pythagorean theorem has to do with the areas of the shapes that form the triangle. So what's the area of this one here? Okay, so we have an area of 24 plus an area of what? 14. So what does that equal for us?
Oh.
That equals an area of 38. Okay, all right. Take the square root of 38 in your calculator.
Oh, I got this. 6.16.
We couldn't make a square 10.6 out of that, and if we don't know either of the two measurements, we couldn't draw something off of that because we have no idea what this length is here. Or is it short? Is it medium? Is it long? How long does that come off? We don't know, because the whole point of this theorem is that it's based off of perfect squares that come off of the outside. So we wouldn't actually be able to use that math problem to solve that. Does that make sense? Okay? All right, good. Okay. All right, fantastic. You guys are good with this, right? You solid here? Okay. All right. Okay, I don't think we need to do any more of these. All right, so let's talk homework. Ready?
Let's do it.
Homework, and you got like 27 minutes to work on it, okay? All right, go back to page 2.
Uh-oh.
Go back to page 2. I want you to circle on page 2 numbers 4, 6, and 7. Page 2, 4, 6, and 7. Okay, page 3. Okay, one more time. Page 2, 4, 6, and 7. Page 3, 11, 15, and 16. Page 10. I'm sorry, not page 10. Your page is 4. Sorry, I'm looking at mine. Page 4, numbers 4 and 5. And then all of these.
Oh, it's
There's 8 right. That's a total of about, what, 14 questions I gave you?
About 200.
And you have 25 minutes.
This is due. This is like
Monday.
I just hear the I just put it on.
I'm getting pretty familiar with your All right, everybody got what they're doing for homework? Any questions? Okay. Equal bars are required, equal signs are required, variables are required. Okay? That's what I'm looking for. Get in the habit. Hey, real quick, look up here. Shh, real quick. On a question like, let's take this one right here. On a question like this one right here, you'll notice that I did not show the subtracting of the 81 here and canceling and the subtracting of the 81 here, right? Did you notice that?
Yeah.
Right? Because that's how we're moving forward. I don't want to see all of that as we're going forward. I want it to be clean and neat. I want to know you know how to do it, and I needed a place for those of you who struggle with that for me to say, hey, we've got to go back here. But now we've already gotten to the point where I'm saying, I don't want to see all of that in here, okay? So nice, clean, neat steps. I do want to see your square roots, though. That's important, okay? All right. You are off and running. Feel free to work with whomever you so choose.